Hello and welcome to another lecture of Introduction to Astrophysical Fluids. In this lecture, we will discuss the dynamics of accretion disks in astrophysics. Before starting, I try to tell you a very important point, that is that here in this context of accretion disk, we will do some modeling. And when we will do some modeling, sometimes it may happen that the steps are not mathematically rigorous. It is done only, so at that point we have to remember that we will try to match some our results or our mathematical structure or model with some known phenomena or observed phenomena. Okay, and that's why if sometimes something is reasonable from our practical point of view, that means from our observational knowledge or some common sense, okay, then we will not really abide by the mathematical rigor 100% at that point, and we will do something offhand approximately. But I will tell you, there will be no secret or no hidden message of this type of approximation, where whenever there will be approximation I will tell you explicitly. But finally the goal is to find something or to recover something which we already observe, even even if not exactly, at least moderately exactly. Okay, so that's our motto or our objective for this thing. Another point is that in case of the accretion disks, okay, there will be a lot of mathematical steps. So in this course, it is not our objective to learn all the detailed mathematical steps. Sometimes when I will say in the scope of this course to go through the mathematical steps to learn, please do that. But for example, when I will tell here, okay, some mathematical steps, and I will say that after some algebra, after some steps, in the most cases, this is not really mandatory for you to go through all the steps, but rather you try to understand the final result and the physical meaning of the final result. Okay, and that's something which is important for this course. Okay, however, if you are interested, you can always go through this type of detailed calculation, searching through internet or referring to some books which I have already mentioned, and some elements of the detailed calculation will also be communicated to you, okay, by me. Okay, so don't worry much for these things. I will try to make clear the best possible, okay, the mathematical details. But of course, once again, the objective is not to get lost inside the mathematical details, rather to try to find out the meaning out of the final results. Okay, and even for exams we will not ask you to do calculations to derive something long or something. It will be mostly using the results which will be discussed here to show something interesting or to calculate something or to ask physics questions. Okay, so it is finally important that the picture of accretion disk and the corresponding dynamics, the formation, the stability, okay, the physics behind it should be clear. So once again, we start by recapitulating the basic assumptions. As I said that for analytical convenience, okay, Shakura and Sunyaev, these two people, they propose thin disk models, and for that we need several approximations. The first one is of course the use of cylindrical coordinates, then the disk to be axis symmetric so that for any quantity del theta will be 0. The principal motion of the moving matter, okay, will be considered mostly in the cross radial direction, that is the v theta will be the dominating component of velocity. However, vr will be non-zero, but it is very small. But vr will cause the small radial flow due to viscosity. Okay. Now for Vz, we will assume that to be 0. Okay. And in general, we will also assume that del z is not equal to 0. For example, del rho del z is not equal to 0. But for the velocity components of Vr and Vz, V theta, that will be 0. Okay. Because Vr, V theta, they are small and their changes are also assumed very reasonably to be small. Okay. So if it is not, as I said last time, that think a bit, that you will understand that there should be some deformation in the disk formation, and that is not quite welcome in this simplified framework. Okay. Now with all these assumptions, finally we will go and study the dynamics of accretion disks. Now first, this is nothing but the equation of continuity which comes, and in cylindrical coordinate this is written as del rho del t plus 1 by r del r times rho r vr is equal to 0. Okay. Now this is my question to you. Have you understood why the divergence term has only one term and not the del? So del theta, the term involving del theta is 0. But the term involving del z is not 0, but Vz there will be 0. Okay. So this type of simplifications you can actually check at home. Now we want to get rid of any z dependence. That is because our primary primary assumption, okay, or the premise is that we should discuss the dynamics of a disk whose thickness is negligible with respect to its radial extension, radial dimension. Okay, and that's why any variation about z or something is not really of our current interest. It may be interest for other research topic, but for our case we will just try to see what happens roughly in the plane which is perpendicular to in the plane perpendicular to the z direction. Okay, or that means the r theta plane. Okay, and for that what we will do that we will try to get rid of any z dependence. So we all know that del vr del z is already 0, and so del v theta del z is something which we should be taking care of. Other than that, rho has a z dependence. Okay, and del v z del z is also 0. Okay, now the question is very simple. The question is that how to get rid of that z dependence of rho. One very simple thing is we can do that. We say that instead of rho we will write equations in terms of sigma. So this sigma is not for summation, that can be confusing, but just please bear with it. For instance, that sigma is equal to integration rho dz. Okay, so this is the density integrated along z direction. Okay, so that this is this doesn't have any information about the variation. Already it is integrated over z, so any variation of rho with respect to z will be contained in it. And finally, if we just study the evolution equation of sigma, so then basically in those equations we are actually concentrating what is happening on the plane of the disk. Okay, that is r theta plane. And for that you can actually see that this continuity equation becomes simply, so you just multiply every term with dz and then you integrate over integrate, and you will have del sigma del t, this term, plus 1 by r del r within bracket r sigma vr, that is equal to 0. Okay, so this is a good exercise to do at home. Okay. Up to this point, we are using assumptions, but we are not how to say, we are not compromising anything with mathematical rigor. So up to this is mathematically exact. Okay. Now this was all for the continuity equation. Now for the momentum equation, momentum evolution equation. We know that v theta is the dominant component of velocity. So we are interested in the theta component of the momentum equation. Okay, fair enough. And if we do that, we will see that if you write, so that is some part you can check in the books of vector algebra, vector calculus and vector analysis, that if you write this type of equation, Navier-Stokes equation, in cylindrical coordinate system, and where you don't use the mu to be constant, but you use, if you remember, this form, rather this type of form. Okay, if you remember this, then you can actually see that the theta component of Navier-Stokes equation should look like this: rho times del v theta del t plus Vr times del v theta del r plus Vr v theta by r. Okay, that one term which comes, okay, you can actually show, is equal to mu times del 2 v theta del r2 plus 1 by r del v theta del r minus v theta by r square, plus, now this term is something which comes as a result of the spatial dependence of the coefficient of viscosity, plus del mu del r times del v theta del r minus v theta by r. Okay, now we again integrate over z to have the equations in terms of sigma, and you will see that this equation gives that sigma times the left hand side basically does not change. So if you just check, you will see, but the right hand side changes a bit, and we have already transformed mu is equal to rho times nu, so that we can, we can actually include that also in the integration. Okay, and we will say that the right hand side will be nu times, nu is called the coefficient of kinematic viscosity and mu is the coefficient of dynamic viscosity. So nu times sigma times del 2 v theta del r2 plus 1 by r del v theta del r minus v theta by r square. So this whole thing times sigma times nu plus del nu sigma del r, of course del nu sigma del r, times v theta by r times del v theta del r. Okay, that is something you can actually check. Okay, so this is also a good exercise to check. Now if we here we can do something to find the evolution of the angular momentum of the disk. Okay, because the disk is somehow rotating, so we can be interested in understanding the evolution of the angular momentum, and that can be obtained if you do one trick, that you multiply r times v theta. So you multiply r times v theta with this equation, and you multiply simply r with this equation. Okay, so this is equation 2 and this was equation 1. So that's exactly what I said here. If you do r v theta times 1 and r times 2 and you sum them up, you will have del t of summation of, del t of sigma times r square omega. And what is this? This is nothing but the angular momentum density, right? Integrated over z, of course, plus 1 by r del r sigma r cube. You see, I am also mixing between summation sometimes. Yeah, this is sigma, this is not summation. So 1 by r del r, 1 by r del r of sigma r cube omega vr, and that is equal to 1 by r del r within bracket nu times sigma r cube del omega del r. Okay. Now for a Keplerian disk, we know that omega is just a function of r, and it is, you know how should it look like? That should look like by, so you all know that omega should have, so omega, so if you remember that t square r cube, so omega square r minus cube, so omega should have r to the minus t by 2. Okay, so this type of thing. Now if you do that, you will see that this del omega del r can actually also be written as d omega dr, and you also know how should it look like because of the dependence. Then for a Keplerian disk, you can further simplify this equation to get this. So from this one to this one, I will try to communicate the analytical steps, but this is a bit cumbersome. Do not worry much. Okay, if you want to show that, you can show that, you can enjoy the calculation, but even if in case you are lost in it, do not worry. Okay, we will, I mean, the basic objective is to understand the final result, and the final result is not yet obtained. Okay, so finally what we can see that del sigma del t, so what we get, try to understand what we get. We get an equation for the sigma. So del sigma del t is equal to 3 by r del r times r to the half del r within bracket nu sigma r to the half. Okay, and you see that this is an equation of evolution of the mass for a Keplerian disk. Okay, so now I mean, so actually we needed all these things. Okay, so we needed this equation, and from this we used Keplerian disk formula, and finally we have this. Okay, so although it looks like sometimes it may be thought that it can be directly derived from continuity equation, you can check. Okay, it is not that easy because nu is there, so nu should come from your momentum equation. So it is really obtained after combining continuity equation with the momentum equation. Okay, however, when you will see the calculations, detailed calculations, or if you do that at home, okay, then you will check it yourself. Now if we at this point, so this is the fundamental equation of evolution of a Keplerian disk. Now if we consider that at t is equal to 0, okay, we are now imposing some initial condition. The matter was in the form of a ring at r is equal to r0. Then what happens, that sigma at t is equal to 0 is nothing but m by 2 pi r0, that is the times a Dirac delta function r minus r0. That means the mass is only concentrated at r is equal to r0. That means this is a thin ring. Okay, now if it is the initial condition, then this type of equation finally gives this type of solution, where x is nothing but process of non-dimensionalizing r, okay, by r0. Okay, and r0 is the position where the initial mass ring is supposed to be situated, and tau is nothing but another way of non-dimensionalizing the time, but here it uses nu. Okay, so finally in the solution you can see that the solution for sigma, so how sigma evolves in space and time, okay, that is given by this. So, and also you see whenever there is a tau, there is nu, there is viscosity. So the viscosity plays a very important role in determining this type of equation. So what is this type of equation? There is a, so it's an exponential type of equation which is minus 1 plus x square by tau, and it is multiplied by a modified Bessel function. So once again, don't get horrified by this mathematical mambo jumbos. On the other hand, try to understand what it gives qualitatively. Okay, and because I mean, if you don't know how to calculate analytically, you can always calculate this type of equations numerically. Okay. So this solution clearly shows something very interesting, and that's why we are very happy. If you plot the solution, okay, then you will see that at very initial position that will be, I mean, a peak like this is a very direct peak. Then it starts to diffuse. So this is 0.004, then this is 0.016, then this is 0.064, and then this is 0.256. Now you see that finally it happens. So first it started diffusing. Okay, so basically this says that this solution clearly sees that, and when t increases, it simply says that, I mean, this is not t, this is tau. Basically this is tau. When tau increases, basically it says that this is nothing but when nu increases and t increases. Okay, it is also possible for a given t, if nu increases, we can also have an increasing tau. Okay, so it is in that way. You can see that if we just freeze the time, for example, and if we just increase the I mean, if we just change the viscosity coefficient, okay, for example, then we will see that this type of effect can also occur. Okay, so in this way you can also think that viscosity is something which plays a very important role in I mean, transforming this peak type of mass distribution, I mean ring type of mass distribution, very localized, to a diffused ring, diffused disk. Okay, also if you don't just change here nu is a constant, you just change t, you will see that exponential, okay, also includes this tau. Okay, so and for that basically you will see this broadening. Okay, so this is the mathematical detailing, but just believe at that point that the broadening with bigger and bigger tau is mainly caused by the viscosity coefficient. Okay, and not only that, you will see after a certain time the symmetric nature is already get. So at first it was a bit symmetric, this one, and then it was more or less a bit less, and this one is not at all symmetric, the final one. Okay, the lower one. What is the meaning of that? That is because the whole system, okay, so the whole system doesn't have any net external torque, so the angular momentum should be conserved. But we know that the angular momentum for a Keplerian disk, omega is to the proportional to r to the power minus 3 by 2. So omega times r square should be proportional to r to the power half. And then the angular momentum actually should increase when some mass goes outside for larger and larger r. If the angular momentum should be conserved, then what happens? That the momentum which is gained for some mass which is going outside should be compensated by the momentum, angular momentum lost by the mass which is spiraling inward. Okay, and as the the angular momentum density, or the specific angular momentum per unit mass, okay, increases with r, we can actually say that only a small amount of mass can have large momentum, angular momentum, and vice versa, a large amount of mass can have small momentum. And that's why we conclude that most of the lost mass actually spirals inward, thereby losing angular momentum, and only a very few percent of the lost mass, okay, goes outward. And that's why the disks are less dense outward, and that's exactly what you can see here. So this is somehow the sigma. Okay, so the sigma is getting less and less when you are going to more and more away of the accretion disk center. Okay, So that is something. Now you see that is the picture you have to understand. It is not really that you have to understand every single functional form or something at this point. If you are interested, you can of course go into the detail. But what I am saying, that this is interesting. So there are two things to understand at this point. The first thing is that you have to see that whenever at initial point of time you are giving some ring like very locally concentrated mass distribution, then with time, okay, it is the viscosity which diffuses the whole thing, okay, because if there is no viscosity, then there is no angular momentum transfer, that we discussed last time, okay, and that actually diffuses the whole thing from ring to disc type of thing, okay. Then there is another point, is that some masses are going inside and some masses are coming outside, okay. So now, is it the same amount of mass? There is another one point, that the disk should be maintaining its Keplerianity, and that's why the angular momentum should be increasing with r as root over r, and that's why if the total angular momentum should be conserved, and that is the case because the system does not have any net external torque, that we will see, I mean that we have already seen, there is no external torque in the system, otherwise we should have mentioned, okay. Then the total angular momentum lost by the inward motion of the mass should be exactly compensated by the angular gain in the angular momentum by the outward motion, okay. Now the angular momentum per unit mass is much important for the outward mass. So in order that the two parts to be equal, the amount of mass involved in outward going motion should be much less than the amount of mass which is spiraling inward, okay. So you understand, it's simply that A times B is equal to C times D. Now if B is greater than D, okay, then A must be less than C. As simple as that, okay. So if you understand these two aspects of accretion disk dynamics, then this is already a good start, okay. So at this point I will stop this discussion, and in the next discussion I will discuss a little bit about the steady disks, okay. But before that I will just show you a very interesting picture, okay, which is taken by Hubble's Space Telescope. Here you can see, so this is the ground picture. So here you can see something very prominent occurs, and when you just zoom and take proper picture, you will see that this is nothing but a dust accretion disk, which has a diameter of, can you imagine, 3700 light year. This is the diameter, okay, and it is around, so here at the very center you can see something like a diamond, okay, something is glittering. And what is that? This is nothing but a huge 300 million solar mass black hole. Of course you can say that we cannot see the black hole, that's true. So this is just the radiation from the horizon, okay, of the black hole which we can see, okay. So this simply says that the existence of black hole, at the proximity of this thing, this is the horizon of the black hole which you can see, they're not the black hole, of course. And so you see that this is a practical this is a real image of an accretion disk around a black hole, and you can see that what we are just discussing, okay, the image which was developed in our mind is somehow very, very close to what we see in reality, okay. Now next part is the properties of steady disk, okay. Now it is true that I mean, till now we have been discussing the evolution of disk, and we have seen that starting from some. So if we assume, that was also an assumption, that initial mass was in the form of a ring, then how it got diffused by the virtue of viscosity. Okay, now we will see that if the disk reaches to some steady state, then what happens. Okay, so that what I mean, we discuss now that we seen the formation and the evolution of a disk. Now we search for the possibility of the disk in steady state. So that means we would like to search for the time independent solution of the disk evolution equation. Okay, that's a routine process for physics. Okay, but before that, let us consider the R and Z component of the Navier-Stokes equation at steady state, and we will see something very interesting. We will fetch something very interesting from that. Last time we neglected those two components just by saying that VR and VZ, they are very small. Actually VZ is 0, so we really don't have anything very interesting for the evolution equation of the corresponding momentum. But here we will again fetch them both, and we will see that something very interesting, I mean, may be concluded. Okay, so assuming that the disk mass is negligible with respect to the mass of the central compact object M, for example the black hole mass or the neutron star mass, which is at the center of attraction, and also that Z is very less than the the height of the disk, or the thickness of the disk is very less than the radial dimension of the disk. That is the classical thin disk approximation. Finally we get that VR times del VR del R minus V theta square by R is equal to minus 1 by rho del P del R minus GM by R square. Okay, of course the del T term goes away. Okay, and also the Z component gives us simply this minus 1 by rho del P del Z is equal to GMZ by R cube. Okay, so these two expressions, for example this one and this one, these two expressions are actually obtained. Okay, this one not really, this one is quite easy to obtain. This one is obtained after this approximation. Okay, you have to just check, okay, yourself the calculation, and I think that this is quite an easy calculation. Okay, so in these two equations we neglect the viscosity, because we have seen that although viscosity plays, sorry, maybe it was not, yeah, okay, so maybe I was not sorry. Okay, so just I'm repeating this thing. So this one was the rth component, radial component of the momentum equation. This one was the Z component of the momentum equation. Okay, and in this one, as the Vz is 0, this simply says that the pressure gradient force is exactly balanced by the gravitational force. Okay, although here the gravitational intensity is calculated under this approximation, Z is very less than R. Okay, in these both equations we have neglected the viscosities. Okay, although viscosity plays a very crucial role in the radial motion of the system. Okay, but this is only, this is only for, like becomes prominent when we are talking about the angular, we are talking about the evolution of momentum in the theta direction, theta cap direction. For the r cap direction and for the z cap direction, really the viscous terms are not of importance. Okay, that is something very important in modeling. We have always keep an eye open to understand at which level which terms are important and which terms are not. Okay. Now we assume that h is the thickness of the disk, which is also a very small quantity. then approximately we can say that the del P del Z, that is the change of pressure as a function of Z, is a linear function of Z. This is a fair assumption. So that is nothing but P by H. Okay. And then you can say, using this one and using this last equation, you can say finally that P by rho H almost of the same order of GmH by R cube. And if you do this correct calculation, one line calculation, you will see H square by R square is of the approximately equal to R times P by Gm rho. Okay, and this is very less with less than 1. Okay, because this is nothing but H square by R square, and H square by R square is very less than 1 by thin disk approximation. Okay, now from 1 we can compare two terms. In 1 we have two terms in the right hand side. One is the pressure gradient force, another is the gravitational force. If we do that, you will see that the ratio of these two is roughly also equal to PR by Gm rho. Is exactly equal to this, and this is then also very less than 1 in thin disk approximation. That's why we can actually assume that this term is dominating over this term, so we just neglect this term. And also this of these and these terms we can forget this term because VR is very small with respect to V theta. So finally the R component or radial component of the evolution equation, momentum evolution equation, simply gives us this, and this is nothing but Keplerian disk approximation. So you see the conclusion is very interesting, that a disk can be assumed to be Keplerian when the pressure gradient is neglected with respect to the gravity term. Okay, and this is consistent with the thin disk approximation. So if the disk is such that the pressure gradient force cannot be neglected with respect to the gravitational force, then Keplerian disk is a approximation is a non-reasonable or unreasonable approximation. Okay. Now finally we consider the steady state condition of the basic equations of disk evolution 1 and 3. Okay, that means the continuity equation and the evolution for the angular momentum equation. So now if you just say that the explicit time dependent terms are 0, then you will directly can show that R sigma VR is equal to C1. So I can just show you once again, there is no problem in case you forgot. So this, in this equation at steady state, this is 0. So this is 0, 1 by R goes away. So this thing within this bracket is a constant. Again, if you go to equation number 3, this term is 0 at steady state. So you have del R, you have this sigma R cube omega VR minus eta sigma R cube dl omega del R or d omega dr, okay, is equal to constant. And that's exactly our conclusion over here. Okay, we call the first constant as C1 and the second constant as C2. Okay. Now note that the mass loss rate is nothing but minus, because there is a loss rate of course, 2 pi R sigma times dr dt. Okay, this is because if you just think that the mass is lost like this, so there's a cylindrical shells like this, then you just take infinitesimally extended cylindrical shells like this, and you will see that the mass inside this will be nothing but 2 pi R sigma dr, and mass per unit per unit time, the change in mass will be 2 pi R sigma dr dt, and dr dt is nothing but VR. So the mass loss rate is nothing but minus 2 pi r sigma Vr. Okay. And this is m dot. Then we know r sigma Vr is constant C1. So m dot is equal to minus 2 pi C1. Okay, which is also constant. So the first thing is that for our consideration, at steady state for an accretion disk, the mass loss rate is a constant. Okay. Secondly, if we assume that at the surface r is equal to r star of the gravitating body, that means at the radius of the central body, for example the neutron star or the compact star or the black hole, the matter is dragged into a rigid rotation process. Okay, and then d omega dr is constant there. Okay, that's a fair, reasonable approximation. Then you can just, using this expression, you can just express C2 is equal to minus m dot by 2 pi gmr star whole to the power half. Okay. Now you see again, both in C1, so C1 is this one and C2 is this one, they both are proportional to m dot. Okay, and m dot is something then so now just using the value of C2 in this equation, finally you can find an expression for expression relating m dot and nu sigma. Okay, so you see nu sigma is equal to m dot by 3 pi times 1 minus r star by r to the power half. So this is one result which you can show starting from these two equations. You first show this one, and then using this condition you evaluate C2. These are very good homeworks. Okay, and then putting C2 over here, you can just try to derive this equation. Okay, now even more interesting is the part that m dot is proportional to nu. So if nu is increasing, then your m dot is increasing. That means the system viscosity is higher, the mass loss rate is higher. Okay. And finally, so that was about the mass loss rate, but finally, even before starting the approximation, the dynamics of the accretion disk, we said that how really one detects the accretion disks, that is by detecting the radiated energy in the form of X-ray. Okay, so now we try to calculate, although approximately, we try to rather estimate, okay, the energy loss rate by dissipation. And here you will see that we calculate the rate of energy dissipation by viscosity, and we will see what is that. Okay, so for weakly compressible fluid, analytically one can actually show roughly that the rate at which energy is dissipated from a fluid by virtue of its dissipation is given by minus dE dt, which is equal to integration mu r square d omega dr whole square dz, and that is exactly equal to, for our that is roughly equal to, for our case, nu times sigma r square d omega dr whole square. Finally, putting this value, this thing, okay, so dE dt you get, and so you know what dE dt is. So finally you will see that minus dE dt is equal to 3g m dot by 4 pi r cube times 1 minus r star by r whole to the power half. Okay, so once again you can see here basically you have this expression for nu sigma. Okay, and here you have an expression for dE dt. So here you have a sigma and nu, so you just substitute this value of nu sigma over here and you will have this expression. This is quite easy to understand. And what is the marvel of this expression? Can you see anything interesting? Well, I can see. You see, this is proportional to m star and m star is proportional to eta, right? The viscosity coefficient. So it means that the viscosity coefficient is higher, so the viscous energy dissipation rate is also higher, which is intuitive. Now the total energy emitted per unit volume by viscosity is given by then this L. And that is just integrated from R star to infinity. R star means that is the surface of the small compact star on which finally all the mass are getting accreted. Okay. Integration minus dE dt times 2 pi r dr, and finally if you calculate you will find a fantastic result, which is gm m dot by 2r star. M dot is a function of nu, so L is a function of nu again. Okay, and you see what this is. This is nothing but the half of the lost gravitational potential energy by the mass lost from the less dense star. So half of the potential energy which is lost by the mass, okay, which is now accreted, okay, to the compact star, is converted to heat by dissipation. What happens to the half? The other half? Well, this is also very easy to understand. This basically contributes to the kinetic energy, and you can actually calculate that. Okay, kinetic energy to the disk. Okay, if you can understand that, you can simply see that the total gravitational potential energy lost now gets converted into two classes. One is the kinetic energy of the disk, one is the heat energy or the radiated energy, and that's exactly the energy what one can see as a compact source of X-ray, for example. Okay, now an interesting thing is that people, when they start estimating this type of energy, I mean, for example, if they use this type of formula, L is equal to this, and then use this kinematic viscosity, then they estimate that from normal kinetic theory, they see that the L or the energy emitted is much lower than what is really observed. That means the kinetic viscosity or the viscosity coefficient, which is calculated kinetically or kinematically, is not, which is calculated from kinetic theory, is not sufficient to account for the energy. Okay, and that's why it is proposed that it is a resultant viscosity coefficient, which is the kinematic viscosity coefficient plus the turbulent viscosity coefficient, okay, is actually sufficient to account for the observed energy dissipated from an accretion disk. Okay, and this thing then opened a new domain of research, that is the efficiency or the efficiency of transport of angular momentum by turbulence. That means turbulence, what it does, it adds to the efficiency of the viscosity, okay, resultant viscosity of the medium, thereby making the process, the angular momentum transfer, much more efficient. Okay, so that was all about the accretion disks, which lies in the scope of this course. The accretion disk is a matter of ongoing research, of course, and if you are interested, you can check out different papers, works, videos over internet. Nowadays you have millions of resources of accretion disk, and of course if you always have good physics questions, do not hesitate to share with me. I will be happy to answer you. If I do not know the answer, I will also think. Okay, and thank you once again for your support. Okay, and I always think that astrophysical things are best understood when you will see the images and the videos. Okay, so do that, And so in the next discussion, so that was all about this accretion disks in astrophysics. In the next discussion, we start about the behavior of a compressible fluid and how it reacts or how it responds to a perturbation to this medium, and thereby introducing sound waves, shocks, and other things. Okay, thank you very much.